18E, Implicit Differentiation. This is the lesson for HR students only. Let's look at what an implicit differentiation is. What are the differentiations we have done in the previous lessons? In the previous lessons, all the differentiation we have done is called explicit differentiation. Let's recall. All the functions we learned in the preceding lessons are written as y equals f of x. When you can write a function as y equals f of x, then you look for the derivative function, y prime f prime x. So this is called explicit differentiation. What is implicit differentiation? We do have those equations in which we cannot isolate y from x. So we will give you guys more examples later on for implicit differentiation. So let's recall dy over dx. This is the Leibniz notation for y prime or f prime x. When working with implicit differentiation, dy over dx is often the preferred notation. Let's use a very easy example to show the difference between the explicit differentiation and implicit differentiation. Let's consider the relation y squared equals x. We say this is defined implicitly because it is not an expression in the form of y equals f of x, because this is y squared equals x. If a relation can be written as y equals f of x, this y should have degree 1 rather than square. But we can solve for y and define this relation explicitly as y equals positive negative the square root of x. Square root of x can be turned into a power form, which is positive negative x to the power 1/2 equals y. After we rewrite y equals positive negative x to the power 1/2 explicitly, we can find a dy over dx when x equals 4 using the differentiation rules we introduced before. So for y equals x to the power 1/2, its derivative should be 1/2 x to the power of negative 1/2, which also can be written as 1 over 2 root x. Or this one, y equals negative x to the power 1/2. The derivative should be negative 1/2 x to the power of negative 1/2, which is negative 1 over 2 root x. So for each case, I can find the particular gradient of the tangent to the curve at x equals 4. So the first one will give me y prime equals 1 over 4. And the second one will give me y prime equals negative 1 over 4. So anyways, the y prime can have two solutions, positive, negative, 1/4. Let's apply the implicit differentiation to see if we can get to the same answers. Implicit differentiation, what should we do? Remember, even I don't want to isolate x, your y is still a function of x. So the implicit differentiation chain rule will always be applied. Y squared, this is a composite function because your base y is a function of x. Chain rule, d outside, d this is square, 2y. 2y to the power 1, power rule, d outside times d inside. What is my inside? The base function. The base y is a function of x. But this time we don't put down y prime. We prefer to write y prime as dy over dx because you want to have very clear view on the expressions. So you don't want the y prime to confuse you later with y to the power 1 in the entire derivative function or derivative equation. So then we differentiate the right side. Differentiate x should be 1. Then dy over dx equals 1 over 2y. Look at the implicit differentiation. This y prime or dy over dx can be expressed in terms of y. It's okay. Right now I need to find the particular gradient at x equals 4. But I don't have x here in the derivative expression. So I need to change this x equals 4 value to the y value. Since y squared equals x, so y squared equals 4. Y equals. So when you solve for y, you really need to realize y can be positive, negative square root of 4, positive, negative 2. So y can be positive, negative 2. Plug in. Don't you think it will produce positive, negative 1/4? So after we applied the implicit differentiation, we still can find the same results. So for this relation, if I want to graph the tangent to the curve at x equals 4, I can graph too. If you guys use decimals, those technology graphing tools to help you, when you graph it, this graph look like this one. When x equals 4, you really can graph 2 tangents. One tangent is here, the other tangent is here. So one tangent has the positive slope 1/4, and this tangent to the curve at x equals 4 has negative slope, negative 1/4. I hope you have got some idea about the implicit differentiation through this example. However, this example is so easy because this example can be differentiated by both explicit and implicit methods. The implicit differentiation is a very, very important method for you to know, especially when you are not able to isolate y from x in a relation or an equation. It is not always possible to define a relation explicitly. For example, here is an example. There's no way for me to isolate y from x to form y equals f of x, this form. Like this case, we must use implicit differentiation to find dy over dx. Explicit differentiation won't be working for this type of the relation. Implicit differentiation is a more formal and a convenient method of finding the differentiation of y for the relation in the form of f of x, y equals 0, in which y cannot be isolated. Right now, let's practice the implicit differentiation skills. Example 1. If y is a function of x, find all those differentiations implicitly. Finding the differentiation for y to the power 4. Y is a function of x. You have to remember this one. Therefore, chain rule must be applied. So y to the power 4, the outside, 4y cubed. Then the inside, d the base y, should be times dy over dx. Don't put down y prime. Put on dy over dx. This is the preferred notation for implicit differentiation. Let's find the derivative of 1 over y squared. So if you want to find this differentiation, the first one is we need to change this one to the power form. So it's y to the power of negative 2. So I need to differentiate this one. Chain rule. Negative 2, y to the power of negative 3, the outside, times the inside. For this one, it's a little bit more complex than a and b. Why? Because there is a product of two functions. So we also need to apply the product rule. So this one is u times v. When you look for its differentiation, you need to differentiate u to x. Keep the v plus keep the u. Differentiate y cubed. When you differentiate y cubed, chain rule, 3y squared times dy over dx. The outside times the inside. If you want to simplify this one a little bit in a kind of, more organized way, it should be 2xy cubed plus 3x squared y squared dy over dx. Find dy over dx in each more complicated equation in example 2. Let's look at this one. There's no need to isolate y, even though you can do this one in this case. But I don't want to isolate y. I will apply implicit differentiation method to find dy over dx. So first, you need the sum rule. The differentiation of the left side, which is the sum of two functions, is equal to the sum of differentiation of each function in the sum. So 3x squared, differentiation should be 6x, plus 2y squared, y is a function of x, you need to apply chain rule. So 2 differentiate y squared, 2y, the outside times the inside. Differentiate the right side. The right side is a constant. The differentiation on the constant is always 0. Solve dy over dx in this equation. Just like solving the x in a linear equation. So 6x plus 4y times dy over dx equals 0. 4y times dy over dx equals negative 6x. Divide both sides by 4y. Therefore, dy over dx is negative 3x over 2y. So this is the derivative function for this relation. Let's look at the second one. So we need to apply the sum and the difference rules. Product rule for this term. So it should be differentiate this one, 2xy plus x squared dy over dx plus 6x squared minus differentiate this one, 3 dy over dx. The differentiation of 9 should be 0. Let's solve dy over dx from this equation. We can have x squared minus 3 times dy over dx, then equals negative 6x squared minus 2xy. Divide both sides by the coefficient of dy over dx. So dy over dx equals negative 6x squared minus 2xy over x squared minus 3. And I hope that you know this answer is the same as 6x squared plus 2xy divided by 3 minus x squared. I just divide the top and the bottom by negative 1. We have another 2 examples in example 2, C and D. I hope you can pause the video here and try to apply the implicit differentiation skills to find the dy over dx from each equation yourself and check your answer with my answer later on. So C, let's differentiate this one. So this one, we need the quotient rule, or change this one to x times y to the power negative 1 plus y cubed equals 4. I try to avoid using the quotient rule. It's a little bit too tedious. So I change this one to the product form. Then I will use the product rule to differentiate x times y to the power negative 1. So differentiate this one should be differentiation of x is 1. So y to the power of -1 plus x -1 goes to the front, then y to the power of -2, then dy over dx. Differentiate y cubed, 3y squared times dy over dx. Differentiation of 4 is 0. Solve for dy over dx. So let's organize this expression to a better looking way. So it's 1 over y minus x over y squared dy over dx plus 3y squared dy over dx equals 0. So combine the like terms. We can move those two terms to the other side and swap both sides of the equation. So we can have x over y squared minus 3y squared dy over dx equals 1 over y. Then dy over dx equals 1 over y divided by x over y squared minus 3y squared. Simplify this complex fraction by multiplying the top by y squared and multiply the bottom by y squared. So we can have y over x minus 3y to the power 4. So this is the derivative function for this relation. Okay, the last one in example 2. So we can differentiate this one. This one should be 6xy plus 3x squared dy over dx. Then plus 4y times dy over dx plus 2/3 dy over dx. The differentiation of -3 is 0. The differentiation of 0 is still 0. Then solve for dy over dx. So combine those three like terms. It should be 3x squared plus 4y plus 2/3 dy over dx equals -6xy. Then divide both sides by this one. So it should be -6xy over 3x squared plus 4y plus 2/3. If you don't like this fraction, I can get rid of the denominator in this fraction. I can multiply the top by 3 and multiply the bottom by 3. So dy over dx can be equal to -18xy over 9x squared plus 12y plus 2. Okay, this is the solution for dy over dx. Example 3. Find the equations of the tangent and normalize to x squared minus xy plus y squared equals 7 at the point -1, 2. So we need to find the particular gradient of the tangent to this curve at this point first. So anyways, we need to find dy over dx from this relation. We need to apply the implicit differentiation scales. So it will be 2x minus product rule for the middle term should be y plus x times dy over dx plus 2y times dy over dx equals 0. Differentiation of a constant is always a 0. 2x minus y minus x times dy over dx plus 2y times dy over dx equals 0. Combine the like terms. 2y minus x times dy over dx, and isolate these two terms from these two terms on the left side. So it's y minus 2x. So dy over dx equals y minus 2x over 2y minus x. Find the particular gradient at -1, 2, at x equals -1, y equals 2, this point. So let's replace x with -1, replace y with 2. So it should be 2 minus 2 times -1 2 times 2 minus negative 1. So the answer should be 4/5. And this 4/5 is the particular gradient of the tangent to this curve at x equals negative 1, y equals 2 at this point. So when we want to write down the equation of the tangent line, we can use the slope point form. So y minus 2 equals 4/5 times bracket x plus 1. What is the normal line? We did not introduce the normal line yet, but I can just, give you guys some heads up. We will introduce the normal line in the next unit. So once you have a tangent line for any curve, so the normal line is the line which is perpendicular to the tangent line and pass through the point of tangency. So the blue one is the tangent. The red one is the normal line. So it's perpendicular to the tangent line. Two lines are perpendicular to each other. So the slope of the normal line should be the negative reciprocal of this slope of the tangent line. So the normal line should have the equation y minus 2 equals negative 5/4 bracket x plus 1. Try to practice your implicit differentiation skills through your homework questions. This is the end of this lesson.